Okay, students, so far so good. Now is coming another question. You are asked to find the inverse of this matrix A. Basically, in order to find the inverse of a square matrix, there are different kinds of approaches. One is using Gauss-Jordan elimination method, and the other is using adjoint approach. There is also another approach, basically, but for the time being, let me show you how the inverse of this matrix can be obtained by using adjoint approach. So the idea is as follow, so let you follow me please. What we need to do is first we have to determine the determinant, students, because if the determinant of this comes to be 0, it is said to be a singular matrix. So instead of proceeding to the next steps, we better stop here saying that the matrix is not invertible, or saying that the matrix is a singular matrix. So whenever you start a joint approach, what you need to do is you have to check first whether the determinant is different from 0 or not. So let's now calculate the determinant of this one. As I said earlier, in order to find the determinant of this, you do have different options. Actually, we are not having 0 entry over here. So how do we have? We could have selected that row or that column having 0 entry. But we don't have, unfortunately, so we can use directly first to expansion. So using first to expansion, students, you can assign plus minus here. So for the plus 1, you have the plus minus 2, which actually is minus 2, then you delete the first row and the first column. So in doing so, you will get a certain some matrix determinant, and that is negative 11, 7, negative 34, 21. And when you come to the second, you are having minus here, so you'll take minus 8 and then delete the first row and the second column. Then 3, 7, 9, and 21 are left with. So here I wrote. And finally, since you are taking positive for negative 5, positive negative 5 is negative 5, so delete the first row and the third column. So you're left with 3, negative 11, 9, and minus 34. So students, the determinant of these three 2 by 2 sized matrices can, you see, enable us to find the determinant of matrix A. So here I just have written them as you see. So what I need to do is try to multiply negative 11 times 21, and it's going to be negative 231. And I took minus 2 as it is. Negative 34 times 7, you look, that is negative 238, because of having minus in front, turns to be plus. So minus 8 is directly taken. Now 3 times 21 is 63, and 9 times 7 is 63, so having minus in between enable us to have 0. And do the same for these two, because minus 5 is taken. Look, 3 times minus 34 is negative 102, plus 9 times minus 11, negative 99, but having minus in front makes this to be plus. So dear students, when you operate this, you will obtain 1. So clearly, you obtain now a non-zero value here. So this shows you that this matrix A is invertible. That is to say that it is non-singular matrix. Or in another way, we can obtain an equivalent 3 by 3 matrix, so that the product of these times the one we are going to obtain can make an identity matrix of size 3 by 3. Now let's proceed how we can find that. So the next step is to find the 9 minors. Students, we do have 9 entries here, so we need to find the 9 minors within this matrix. So these 9 minors are directly obtained by using this approach. What you need to do is the first minor, M11, is the minor for A11 for minus 2. So in the case of this, deletes the first row and the first column. You are left with negative 11, 7, negative 34, 21, as you see. So try to multiply negative 11 with 21 and subtract the products here, 7 with negative 34, you will obtain number 7. So the second is a minor of A12, that is to say 8. So to find the minor of 8, what you need to do is delete, look here, the first row and the second column. So delete the first row and the second column, and you are left with 3, 7, 9, 21. You see, 3, 7, 9, 21, and this makes 0, students. When you come to this one, look, the third one, M13, this is an element obtained at the intersection of first row and third column. So please try to delete the first row and the third column. You are left with 3, minus 11, 9, minus 34. So as usual, try to calculate the determinant again. You will obtain this to be negative 3. So students, you need to do this sort of approach for all these 9 entries. So these outputs are called the minors for the given entries, okay? So as you are doing this in such a way, you are going to have these 9 m values. Now what comes next is cofactors, right? We have to determine cofactors, the cofactors of these 9 entries, because having that is very important. The cofactor of every element which has been represented by Cij is the plus or minus of the minors. What matters here is the even or the oddness of what? This sum, I plus j. If I plus j comes to be even, then -1 the power of even is +1, so the cofactor is going to be equivalent to the minor. But if I plus j comes to be negative, students, -1 the power of negative number makes negative, so the cofactor is going to be negative of the minor. So in short, what I would like to tell you is a cofactor of every entry is a plus or minus of, you see, the minor, depending on the location of each entry. So for instance, in the case of C11 students, C11 is, you see, a cofactor for -2, because -2 is the first an element obtained at the intersection of first row and first column. So as you know, 1 plus 1 makes 2, so -1 the power of 2 makes 1, so C11 is basically the same as M11. We already determined M11 as 7, so this 7 can also stand for C11. Now let's come to C12. Mind you that 1 plus 2 is 3, so -1 the power of 3 makes negative. So you are having negative M12. In fact, M12 is 0, as you see above, so -1 times 0 is 0. But had it been different from 0, we could have considered the negative into account. So do like this for the rest. Look, for the rest, C13 is basically equivalent to M13 because 1 plus 3 is 4, so it is even, so it's equivalent to that. But when you come to C21, look, C21, 2 plus 1 makes 3, so -1, the power of 3 is negative, so it's going to be the negative of M21. We know that M21 is already obtained, it's -2, now have negative in front, so negative changes to +2. In such a manner, we have to list every cofactor for each entry in such a way. Now what comes is, you see, when what comes next is presenting the obtained cofactors in terms of matrix form. So let's call that to be C. As you see, we just have labeled, okay, each cofactors obtained according to their place: C11, C12, C13, C14, C21, C22, C23, and C31, C32, and C33. See? Once we have that, now let's define what adjoint of a matrix is. We know that the adjoint of a matrix is the transpose of the cofactor, right? So we have to consider the transpose of this. Taking the transpose of this is so simple. It's a matter of changing row to column and column to what? Row. Just interchange. You see these two. So the adjoint matrix is the transpose of the cofactor matrix. That is, adjoint of A is transpose of C, the cofactor. So look, what has been written as a first row is written as a first column, as you see. Second row, 2, 3, 4, has been written as second column, you see. So again, third row has been written as, you see, third column. So this is a transpose. Now it comes next is the final one, which is actually the inverse of the matrix. Students, the inverse of the matrix is the adjoint of the matrix divided by its determinant. So here it is. We are having now here adjoint of the matrix, as you see, directly copied from above, and the determinant of A is already obtained. It's 1, so it's a matter of dividing every entry by 1, so every entry comes, as you see, directly. So the obtained inverse is going to be like this. So what is the idea behind this is, if you multiply matrix A by its inverse, student, by the one obtained here, an identity matrix of 3 by 3, which actually is a matrix like 1, 0, 0, 0, 1, 0, 0, 0, 1 can be obtained. So this is going to be, the last matrix is going to be the inverse for the first. Not only that, the first can also be the inverse for the last one. If two matrices are inverse, if one matrix is inverse to the other, we can say that the matrices are inverse to each other. This is the idea. This is a way you need to find inverse by using adjoint approach. I hope you have understood it.